of how we've used some of the functional flows approach actually in the FERC licensing process. So Eric gave a nice overview. He talked about how there's a lot of different tools in the toolbox. There's a lot of different groups that are working on environmental flows. His list did not include a lot of the federal stuff, so I'll provide an example of how we've used that in the FERC licensing process. And so, like most people in the room, these are hugely collaborative efforts, interdisciplinary efforts, interagency, lots of universities involved, and nonprofit organizations. And so I'm going to be pulling from examples of some work that I've been involved in. These are some of the folks that I've worked with on the stuff I'm going to talk about, and here's some of the papers that will give more detail about what I'm going to talk about, but I'm just going to give a cursory overview at this point in time. Okay, so like you guys have been hearing, there's a whole variety of environmental flow methods that have come out in the last several decades as we've looked to sort of restore some of the alterations in our stream systems. And most of these stem from the idea of a natural flow regime and species being adapted to a natural flow regime. So you've heard about this set percentage of flow that Eric alluded to. Rafi just talked about the Aloha approach. Each of these is a different approach to going to it and will have a different applicability in a different region. One of the things that we ran into when we were doing a lot of work within the FERC licensing process is that highly developed rivers and highly modified watersheds have such limited flow allocations that the idea of trying to restore a full natural flow regime or even a downscaled flow regime is just simply not feasible. So we started looking for another approach to how can we design flows with these really limited flow allocations to really maximize the functionality and biodiversity in our streams. So one approach we took was this idea of a functional flows approach. The idea is that we're going to be picking out components of the hydrograph that are specifically linked to and support natural disturbances within the system. So for example, on the upper graph here, we know that there are a bunch of abiotic thresholds as we get increasing magnitudes of flows in different times of the year. They promote physical dynamics, peak flows scour sediment in the winter, they help reset the in-stream habitat, and these are really important processes then that happen within the river. Similarly, there are certain flows at certain times of the year that provide ecological cues for native species that have adapted to the flow regime. And so, for example, if you change the timing of a flow, you then might be impacting an ecological, a particular aquatic species or an ecologic species. So there's ecologic functions, for example, that we might want to target in on. And a lot of this really needs to take into account the geomorphic setting. So I'm glad that Eric brought it up and showed that one slide with the geomorphic aspect, because one thing that we need to consider is that as we change flows and put environmental flow regimes into place in certain streams, there's only going to be able to go so far with those impacts if the geomorphology is not there to support it. So I'm bringing this up again here as sort of a token to throw out to the room again that these are processes that we need to consider as well. I'm going to go on and talk more specifically about relationships between flow and species in the FERC process, but I want to throw that out there as something that we should potentially talk more about in the future. Okay, so the idea behind the functional flows approach is that we're trying to target a particular aspect of the flow regime that provides a distinct geomorphic, ecologic, or biogeochemical function. We know that streams are three-dimensional. They have longitudinal variability, lateral variability, vertical variability, and they vary in space and time. And so when we implement certain flows, they also need to be reflective of the natural patterns that occur in space and time. So this blue hydrograph is an example of a natural flow regime from a northern Sierra River. It has low flows in summer here in California, it has high peak winter flows, and it has a snowmelt with a spring recession. And so 4 particular functional flows then are delineated on this graph that each provide an important function within that type of the system. So wet season initiation flows are really important in these systems biogeochemically. They're sort of the first flow that comes in, reconnects the channel with the riparian zone, really kickstarts all that nutrient and cycling that happens, and it also provides migration flows too for a lot of our native fish species. So that might be a type of flow that we want to retain in a system. Similarly, peak flows in the wintertime do a lot of the geomorphic work in our systems. They move sediment, they clean out the habitat, recreate the habitat, scour back the riparian vegetation, and without those periodic high flows, you end up with systems that are become choked with vegetation and very stagnant. The spring recession flow has a lot of ecological importance in our rivers. It provides that transition from high flows in the spring to low flows in the summer, and it provides environmental cues for a lot of spawning, reproduction, outmigration of salmon, and actually some of the new studies that I'll talk about here in a minute are showing that it correlates with a lot of high natural biodiversity within our systems. And then of course lastly, dry season base flows, setting that low season flow at a point that maintains either natural perenniality or natural ephemerality in a system is also really important. And so furthermore, we know here with our California climate, we have wet years and we have dry years. And so these flow events really should not be static from year to year, right? They should reflect what's happening in our climate. Really wet years, for example, then might retain each of these 4 functional flows, but they might be at different magnitudes with a slightly different timing depending on what type of water year we have. So for example, we know that really wet years can be really great years for fish. There's a lot of cold water in the system, a lot of snowmelt coming down, and that can be a wonderful boon to fish. It might not be so much for our native frog species, for example. In dry years, it turns out those actually provide really great habitat conditions for our native frogs. And so the full complement of biodiversity here in our state really becomes a reflection of having this interannual variability. And so from a biodiversity perspective, it's important to maintain that when we set environmental flows as well. Okay, so how do we go about doing this in practice? Well, as you've heard from Eric and others, there is a group where we've sort of looked into trying to figure out how you might define these functional flows for regions of interest. One approach that we've talked about, there's a couple different approaches, is the idea of developing a standard hydrograph for a particular hydrologic stream type, that classification stream type that Eric showed earlier. The idea, each of these boxes, for example, on this unimpaired hydrograph here might represent a different functional flow, and the magnitude or the height of that box, as well as the duration of that flow, the width of that box, then might be set by looking at the statistical variability of an unimpaired system. The timing of when that particular flow occurs within a box then might also be set by the aquatic species needs of interest, for example, an outmigration flow for fish. And so this is one approach that we're sort of starting to look into to be able to come up with a sort of more generic or statistically based functional flows approach for these different stream classes in California. I'm also going to talk about some of the work that's happened a little bit over the last couple of years within the FERC relicensing process, and I'm going to use the spring recession flow component as an example of how we've worked through that. So another idea we had was that in the FERC relicensing process, it's a stakeholder-driven agreement. All of the agencies, as well as utilities and any other stakeholders within the group, will come together to negotiate a natural flow regime. And we were really interested in particularly restoring the spring recession flow component to some of the streams that were altered by dams. The reason we wanted to do so is because this spring recession flow is so ecologically important here in California. It is the one time annually where high resources are coupled with predictable flows, so there's a lot of natural flow in the rivers because of the spring snowmelt, but it's very predictable. It's gradually draining out of these watersheds in a predictable manner that the species then have used to cue into for their native life history. It limits riparian vegetation encroachment by allowing for a gradual decrease in flows down to the center part of the channel. And particularly if these flows can extend out onto the floodplains in our lower elevation rivers here in California, that extended duration of flow allows for nutrient cycling and a whole suite of ecological processes to happen out on the floodplain. And there's a nice study here by Carson Jeffries et al. that discusses that aspect of it. So all of these pieces together then result in high biodiversity within the system, so this made a particular flow component that we wanted to restore back into some of these regulated rivers. Similarly, we also know that if we remove the spring recession in some of these regulated rivers, that we can have really dire consequences for some of the species. So this is an example. The foothill legged frog is a native California species. It's in decline due to dams and regulation. And so consideration must be given to it in the FERC licensing process. This graph here shows what happened in 2011 on the regulated North Fork Feather River, and it's really indicative of a lot of our Sierra and rivers here in the state. So the rivers below, the dams that are in these rivers, they collect the water that's coming down in wintertime. The reservoir fills up, and if it's a wet year, the water then spills out of the reservoir in an unpredictable release over the top of the dam. And so that's what you're seeing here with the red line on the Feather River. And so those high flows in 2011 spilled over the dam, and as soon as they gained control of the dam, then they shut the gates and immediately returned the river back down to base flows. So these regulated rivers often have sort of a flat baseline flow for most of the year, with a periodic spring spill release that comes over the dam in an unpredictable fashion at some point when the reservoir spills. And so that's what you see here in the red line. And the blue line then is the unregulated North Fork American for comparison. And so this abrupt decrease in stage and flow resulted in desiccation of the entire annual cohort of the foothill-legged frog. So we were able to use this then as an example of why we wanted to restore the spring recession in this particular river through the FERC licensing process on the North Fork Feather. And then finally, we also have good evidence in a study that's going to be coming out soon for the importance of the spring recession related to the bug community. So this, we did a study, the upper watershed in gray there is the Yuba watershed, the lower brown watershed is the American River watershed, and we had a series of study sites where we collected macroinvertebrate samples on 5 different rivers across 3 years in August, following some of the basic protocols. And we looked at simple metrics of diversity. This plot shows you Shannon's diversity, for example. And what you can see is not unexpected, but the unregulated rivers that are shown here in blue and light purple, the North Fork American, North Fork Yuba, and Rubicon, all have high levels of diversity and low levels of impairment. And the yellow and dark red squares there at the bottom have low diversity. So we see that the bugs are sort of giving us an indicator of alteration within the system. So we then compare that to some of the key hydrologic metrics that we found within the rivers. And we looked at a similar suite of metrics that gets used in Aloha and some of the other ones, metrics relating to magnitude, timing, duration, rate of change. And used a boosted regression tree analysis to look at which of those factors are most influential over the diversity. So modeling the diversity based on which hydrologic metrics best described that change in diversity with the flow regime. And interestingly, what we found is that the top 7 hydrologic metrics that fell out as being most influential over that diversity index were actually related to the spring recession, particularly the recession duration and the recession rate. And so how long that spring flow is in the system really does impact the bugs. And interestingly, the summer temperatures were a huge indicator as well. So August temperature, variability, and means also seem to be a big indicator for the bug community. So this is yet another indication of just why the spring recession then was so important, and we took a lot of this scientific information back to the FERC relicensing process to work with them on how do we go about getting this change, this new environmental flow put back into the system. So as you know, we can quantify particular flows by looking at their magnitude, rate of change, and timing. And so we focused in on these metrics for the spring recession as a way to predict and figure out a way, how do we put this back into this regulated system? So we looked to unregulated spring recession rates throughout the Sierra Nevada. So there's 8 unregulated basins and subbasins that are left in the Sierra Nevada that have gauges. And one of the things that we found was that despite different watershed sizes, and despite latitude, northern Sierra versus southern Sierra, and despite elevation, there's differences in maybe perhaps the magnitude or the timing of when the snowmelt pulse would happen. But you'll notice that the recession rates, those spring drawdown rates, the slopes of all those lines are shockingly similar despite their location. And so if we look at that recession rate, what we found is that on average, the rate is very consistent across basins. It decreases from 8 to 4% per day, typically, and it's typically very limited. We never saw unimpaired rates that were higher than 20% per day. And this was really consistent across those basins. So this provides us with a quantitative flow metric that we can then use to put into a regulated system. So if I'm going to design a new flow regime in a regulated system, I want the metrics to match what I'm seeing in the unregulated system. So here's an example of what we did in the Rubicon River. And so we would say, for example, start our recession from spill at 700 CFS. That's the control they have at that dammed system and the operations they have for that system. And from 700 CFS, then we would step down at a rate that matches the natural rates we see in unregulated systems. So stepping it down from an 8 to 5% per day. We would limit the steps to no more than 20% per day. So the graph here on the left shows if I was to decrease the flow from 700 CFS down to base flow at 35 CFS at 8% per day. But a dam operator doesn't really want to go out and turn the knob every day, right? So you have to work with the operators. And what they want is they want to be able to adjust the flows every 3 days because that just makes it easier to them. So okay, fine. So we come over and we have a flow schedule then that matches, similar to what they're doing there, where each flow step every 3 days then follows that general trend, but that each step is no more than 20% per day. So in this case then, we're able to design a spring recession flow component within a regulated system that matches the unimpaired rate in a way that we hope will be supportive of the biology based on what our studies have, in a way that works with the operations within that system. Okay, and we were able to do this in a really simple way in Excel too, which made it really easily and understandable for all of our stakeholders that were in the meetings. And so this example then, with this methodology then, by looking at these recession rates by using quantitative flow metrics, knowing that the recession then is so important for the ecology with the studies to really back it up, we've been able to then go forward into many different several different FERC licensing projects throughout California and been able to actually get this written into the negotiated flow schedules that are being written into the licenses for those places. And so here's some examples ranging from down south in the San Joaquin River all the way up to the McCloud River in the north. One of the interesting things that I'm showing here as an example is from the North Fork Feather, that graph that I showed you earlier where the frogs all got desiccated that one year. In that place, what we did is not only did we actually institute a spill recession schedule, which you can see here in the bottom graph, where we're stepping down the flows in a way that will not allow for a gradual recession down back to base flows, but they also implemented monthly base flows that were a little bit more reflective of a natural hydrology, and that's what you can see in the upper graph. So for example, the base flow would be lowest in October and November. It's going to increase in December, a little bit more like a natural hydrograph, and then kind of step down monthly in the springtime as well. So both of these components got written into the FERC license for that particular reach. And the other thing that was really great about this was that in terms of balancing those multiple needs that happens, there's a large boating contingent with American Whitewater that's actively involved in this project. And so we worked with them to take their flow allocation. So we had no flow allocation for environmental flows. There was allocations for hydropower, allocations for water delivery, but the American Whitewater community had won a flow allocation for their boating flows. And they wanted to be able to release their boats at different points over the summer, which actually would have created these unnatural pulses in the summer. And we worked with them to actually stack that water in the springtime to achieve both an environmental boating flow in the spring when it naturally would have occurred, which is that shelf you see at 600 CFS for 15 days, and put that within a spring recession. So we achieved the benefit of both getting an environmental flow allocation and a whitewater boating recreation allocation by working with our stakeholders. Okay, so just to summarize up, basically the idea with the functional flows approach is that we're looking at quantifying and restoring flow components with the greatest link to processes. This is particularly needed in systems that have limited flow allocations where you simply don't have a lot of water to work with. And so we really have to maximize the amount of water for the ecology that we can. The restoration of the spring recession is one example that I talked about where we were able to do this within the FERC licensing process. And in doing this work, one of the things that we found is these quantifiable flow metrics, like a daily recession rate, are the best way to talk about this and communicate this, both in terms of designing an environmental flow, but also monitoring an environmental flow later. And if we can relate those quantifiable metrics to the ecological endpoints, either whether it's BMI diversity or foothill-legged frog breeding, that's going to carry the most weight when we go forward into working with our stakeholders and colleagues in this type of a opportunity, in this type of a system. And so because of that, we really seek these opportunities to engage the stakeholders so that you can come to a more consensus agreement. And the North Fork Feather case is one that really ended up being a win-win situation for most people involved. And so with that, I will finish up, and if there's time for questions, I'll take a question. Thank you.
That's good. How sensitive is your approach, given that we are possibly having a change in climate and we are moving from a snowmelt-driven system to a more extreme event system?
No, that's a really excellent question, and I think that's one of the areas for further study that's applicable to all the environmental flow methods in a lot of ways. And so I think one of the things that we've done is we have actually done some modeling on impacts of climate change and how that's going to shift some of the Sierran rivers in particular. A lot of my work tends to focus in the Sierra Nevada. And what we see is that you do get a shift to a rain-driven system, but there is still snow at the higher elevations. So the timing of that snowmelt might happen earlier. The magnitude of the peak flows might be higher and a little bit more extreme. And so whether or not our species are going to be able to adjust to that is a really excellent question that I think a lot of us don't know. But if we can maintain the pattern using something like a functional flows approach or one of the other environmental flows, and we're retaining the predictability of the pattern, that I think is the case where most of our aquatic species hopefully have the best chance of being able to look for those cues. So that spring snowmelt recession cue, sometimes in dry years, for example, it happens really early. In 2012, the snowmelt recession didn't really exist in in a lot of rivers. And we saw a lot of our species just actually breeding 2 months earlier than they ever had before, because those cues that they were looking for were happening earlier in the year. And so so actually the way we took that into account within the FERC relicensing process is we increased and moved the date when they had to consider ecological flows earlier. So rather than setting a May 15th date where they had to consider spring recession flows, we actually pushed it back to April 1st in the hope that, so that's really kind of all you can sort of do is sort of try to anticipate it and work within that system. But it's a really excellent question and opportunity for a lot more research, I would say.